Okay, welcome to class 11, and today we're going to talk about strings and a little bit more about passing pointers. So let's go ahead and get started. Rather than waste time, let's go ahead and dig into this. So let's start off with strings. So strings in C, you may have noticed when we went through the various data types that C had to offer, that there were things like character, unsigned character, there were integers, short integers, long integers, both unsigned and signed. There were floats, there were doubles, there were long integers, there were, but there was no string type. There was no type that says this is designed to hold a string. But you'll notice in our code that we've used strings like this here, where it says like hello world. That's clearly what in most languages would be considered a string. It's this thing in double quotes. So if there's no string type, but we've used strings in our program, what's going on there? In other words, we want to answer the question, how does C support things like strings if there is no string type? And let's take a look at that. All right, so strings in C are kind of closely related to arrays in that, remember, if you use the name of an array by itself, it evaluates the address as the address of where that array starts in memory. And it turns out that when you have a line like this printf double quote hello world \n end quote, that actually evaluates as an address. So when you have something in double quotes like that, it actually evaluates as the address of where in memory that string is actually stored. The other part of that is, since it just evaluates as where it starts, there needs to be some way to tell when it ends. And the way that is done is by having what's called a null terminated string. So in other words, the end of the string is indicated by a null character. And the null character in ASCII is character 0, meaning all 8 bits are off. That means this is the end of that string. So in other words, it starts at this address and it runs up through wherever the null character is. And the null character is actually being created automatically for us. It's after the new line character that gets put in there with that escape sequence. So in other words, we'll have hello world, a new line character, and then a character 0 in memory. And when printf goes to print that, it basically says, go to this address and print everything up until you hit a null character, but not including the null character. Now, the strings evaluate as an address of where the string starts in memory, and the string is kind of implicitly terminated by that null character. In other words, C doesn't really know how long the string is. It just says, here's where it starts, and print it out until you get, or process it until you get up to that null. And so to store that, though, we need something that can have an array store an address of character data. So there's two options for that. One is that we could use an array of characters, because an array of characters is something that lives in memory at some address. It's all contiguous. The other option is to store that address in a character pointer variable. Remember, pointer variables are designed to hold addresses, so we could stick that string into a character pointer variable and let it hold the address of character data that came from somewhere else. One other thing is that null terminator is really important, because that's the only way that C knows where the end of that string is. In other words, it says the character pointer or the array, it just says, here's where it starts in memory. We need some way to know where it ends. That's what the null character does. Okay, so let's look at a few examples here of some things that are right and some things that are wrong. So for example, character pointer, CPTR, equal hello. Now remember, hello in double quotes evaluates as the address of where that starts in memory. And in memory, this is going to be HE, it's the binary for HELLO, and then C is automatically going to put that null character on the end of that string for us. So in other words, what's going to be stored in CPTR is just going to be the address of where this H starts in memory. We could also make this character pointer work this way. This is kind of the same as what we put up there. This square bracket notation like this, though, does have a subtle difference that really this kind of creates something that's functionally equivalent. But the difference here is that this character pointer here, this one is probably in most systems in a read-only memory segment. This one is probably stored in a modifiable or read and write memory segment. But they both operate as pointers. And you can think of this, though, as an array but it's really a pointer. So if you do size of on this, it's going to give you the size of the pointer, not the size of the data here. But this one is actually an array. And here we've reserved 10 spaces for characters. This is a character array with, where we've reserved 10 spaces in memory, 10 bytes. So H, E, L, L, O, and then the null. And then we have some other bytes after that that aren't having anything put in there. So this gives us the ability to then make that string a little bit longer, add things to it later if we wanted to, change the hello to hello exclamation mark. But notice that we performed a static allocation of exactly 10 bytes. Now, that brings up an interesting question that has to include storage for the null character. Even though the compiler's adding it automatically here for us, we need to include enough storage for that. So if I do something like this, character CPTR 5, well, the word hello, you might think, well, 5 is enough for that because H, E, L, L, O, that's 5 characters. So I'll reserve a space for 5. But notice I did not leave enough room for the null character. And some compilers will just silently allow you to do that. And then there won't be a null. And then if you went to print this or use this string, it wouldn't be terminated by a null because there's not space for it. So always keep in mind that when you allocate space for a string, or at least with static allocation, you need to make the space for the null yourself. Now down here, this is definitely an error. The compiler won't even let this compile. You said, hey, make an array of 3 characters and then stick something that's 5 characters long in it, really 6 if you count the null. And the compiler will say, this is too large to fit into that. But this one, it could let it pass even though there's not enough room for the null. Some compilers will prevent that. Some will give a warning. So some will give an error, some will give a warning, some will just let it pass. Okay, moving on. String assignments, there's some stuff we need to talk about there as well. Then notice in this example code, I made a character array AR. It's got 10 spaces. So that's an actual array of characters that has 10 bytes worth of storage. And then I made this character pointer, which, remember, the square bracket notation creates a pointer to a modifiable space in memory. And I put 10 spaces there. Now, is that 10 spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's only 9 in the written part, but we need an extra space for the null. So that's going to be allocated there with that as well. And then I just made a character pointer called PTR2. Now, down here, AR equal hello. You cannot do a string assignment like that. And the reason being that AR, the name of the array, when used by itself, always says the address of where in memory this array is. And I can't change where that is in memory, so I can't assign that. I cannot do that. So you cannot do a string assignment that way. We could, however, say, hey, go into that array position 0 and set it equal to the character B, which would be ASCII value 66. That's okay, but that's only changing one letter. I could also say, all right, use PTR1, which is also a modifiable array, and go into position 0, which is where this 1 is, change it to a 2, so it says 20 spaces. That's not right, but not the right number of spaces, but I could do that. I could also say point PTR1 at the word hello. That's okay. I could say PTR1 subscript 6, set that equal to A. In other words, 0, 1, 2, 3, 4, 5, 6 would be off the end of that hello that we put in there, but I could set that because it has, actually this would probably be not okay, because notice that we put the address of this hello thing in there, and now we're off the end of that. So we're off in a part of memory that was not allocated for this string. So this would probably compile, but it would be off the end of the array into other part of memory that doesn't belong to the string. So that's why that says danger. Now this one, the thing pointed to by PTR2 equal hello, well, the thing pointed to by PTR2 right now, it's not pointing to anything. It's a random address. Remember, variables in C, if they're uninitialized, they're truly uninitialized. You just have garbage in them. So in this case, we're saying, hey, go to that place in memory and set it equal to this address. And that's going to give you a compiler problem anyway, because this thing is a character. Thing pointed to by a character pointer is a character, and we're trying to set it equal to an address or a pointer to this hello. That's not going to work. But we can do this. We can say take this address that this PTR2 is holding and set it equal to this address of the word hello. That's okay. So look at those again very carefully. and think about what each one of them is doing. It's important to understand how pointers work, how arrays work, and ultimately how strings work. Now, we said that you can't do an assignment like this by just saying AR equal hello. And we're going to actually talk about how you would do something like that in a little bit. How would you actually copy a string into some array like that, or into a character array like that? We'll talk about that here in just a little bit. But before we do that, I want to focus on this strings versus characters and the differences between those. So if I have something in double quotes, that's a string. If I have something in single quotes, like I have down here, that's a character. Now, what's the difference? The double quotes evaluates as the address of where in memory the 2 bytes live, A followed by a null. So it's those two characters are going to be in memory, a capital A and a 0 byte or a null. It's going to evaluate as the address of where that A is. Now, when you use the A in single quotes, that evaluates as the ASCII code value of that capital A, which is 65. So this is no different than putting 65 in your code. All right, so here's some example. Character CH equals single quote A. Totally fine. This is going to be a 97. So we're basically saying make this single byte variable, put a 97 in there when you initialize it. The next one, character pointer ST equal double quote A, that's going to say, okay, make this character pointer that's holding an address of character data, and then put the address of where this A970 live in memory. So the A followed by the null. Now, one thing we can't do, thing pointed to by ST equal single quote B. That's changing that A to a B. So in other words, a thing pointed to by a character pointer is a character. In this case, what's it pointing at? Has the address of where that A lives in memory. So we're saying change that A in memory, change it to a B. So now we have B null instead of A null. But trying to do this, if I say thing pointing to by ST, that's a character pointer. So what's that pointing to? That's pointing to a character. So we're trying to set an address, because that's double quotes, we're trying to set that address into a thing that's designed to hold a single byte. And that address is not going to fit. This is not going to work. It's not going to compile. Now, conversely, if I say ST equal double quote C, that's going to point this pointer at a different string where it was pointing at A null. Now it's pointing at C null. But if I try to say ST, which is holding an address, and try to stick the value for the ASCII value for lowercase c, which would be, what, 97, 98, 99. So I'm trying to stick the number 99 into a thing that's holding an address. That's wrong. All right, so again, look at these. Make sure you understand the distinction between single quotes and a character is evaluates as the ASCII value of it. Double quotes with stuff inside of it evaluates as the address of where in memory that null terminated string lives. Okay, so reading string input, and if you've come to this from Python, there's an input function. In input, you basically have it print out a prompt, you type stuff in, and it takes that and returns that as a string that then you can assign to a variable. Well, getting input in C, there are a number of ways to do that. Let's look at kind of the first way here. And we're going to look at better ways later on in the semester, but for right now, there's an opposite of printf is scanf. And what scanf does is it basically says read formatted input in, and it uses the same kind of format specifiers that printf does. So here I just said print enter string to print out the prompt, and then I did scanf %s, which %s is the format specifier for a string. And then I put the address of where I want that string data to be filled into after as the variable that gets substituted in for that. So in other words, this has one %s, has one variable here. So that variable is the name of an array by itself. It evaluates as the address. It's the address of where I'm going to fill in that string data. And then I just print it out. So again, here's the %s again being used in the printf to print out the string that we just read in. Now, there are some problems with this code though. So this will work, but there's some problems with it. And actually, here, let's just take a quick, let's take a quick break and go to the online compiler thing and try that. And let me switch this around so you can actually see what I'm doing here. Hold on just a second. Okay, so here's this online GDB compiler, and we are going to put that program in here. So we're going to say enter. There's our prompt. We're going to use scanf. Well, we need a variable, so I called that input. I'll make it 100. And then here, scanf. We're going to read in a string format and read that into the input variable, the input array. And then after that, printf, you entered :%s \n, comma, input, semicolon. Okay, so there's my program. Let's go and run it. And notice I have the prompt down here, enter a string. This is a test. Okay, first problem that you may have noticed is it says this, and then where's is a test part. So that didn't show up. Let's run it again and try something else. It's like, was it a length problem? Well, let's try something else. Let's do something that's fairly long like this. Okay, it got all of that. So why did it have a problem with that? This is a test. And the reason it had the problem with that was spaces. And actually, there's another problem with that code. Let's switch back to the thing. We'll come back to that code here in a second. But you'll notice that there's two problems with it. So the first problem is that this buffer could be overrun, meaning that I've only reserved enough for 100 spaces, but scanf doesn't know how much space there is for that thing. It just says, hey, when you start reading characters, fill them into this place in memory at this address. But I could run off the end of this buffer. And if I run off the end of that buffer, I'm now reading characters from the keyboard directly into the memory of this program in places where we probably don't want those things to be. So there's a problem with this scanf that we don't have it bounded. And that's dangerous. That's a security hole in this program. It could also cause somebody to accidentally crash the program. And let's go back to that other program for just a second here and see if we can... Here, let's change the size of this to 10. Let's run it again. So same program, we just changed the size of the array to 10. And now I'm going to put in this is a test. Now notice that's more than 10 characters. And I ran them all together, so it didn't have the problem with the spaces. I'll put an exclamation mark at the end. And then notice that this error got detected. It said stack smashing detected, a.out terminated. So that means that we walked off the end of our reserved memory for this input, and that the compiler caught that, or the runtime for when this thing was run, the compiler didn't catch it. The operating system caught it and said, something bad happened to this program. It went outside of the memory that was reserved for it. So we aborted the program. So the program actually crashed when we actually ran this. And the reason is we walked off the end of that array. So let's solve both of those problems here. So let's switch back to the presentation. Okay, so we want to fix that. And the problem is that we have an unbounded %s here that allows it to be any arbitrary size. There's a second problem that it is not allowing spaces because it's using that as a, what do you call it, a delimiter. It's kind of grouping the things based on spaces. Okay, now here's a fix for it. Notice what I did. I only changed one thing. I have %99s. And what that does is says that allows a string of up to 99 characters. So now it won't overrun. We could never type in more characters than I'll have here, because as soon as I get to 99, it says you're done. Now, why didn't I set that to 100 when this was 100? And the answer is, remember, we still need that space at the end for the null character. So the 99 here leaves enough space for the null plus 99 characters before that. And since we have 100 spaces total, we need to make sure we left enough for the null to go in at the end. Now, the only difference was putting that 99 between the percent and the S. And that 99 allows me to set the width of that. So now I could type in strings of up to 99 characters and not have any problems. I would never overrun that buffer. But there's the other problem, that %s is still using white space as a delimiter. So if I type hello space world, it'll just truncate it as hello and say, well, that's the end of that string. So how do we fix that? So now I've made another change to this program, and now I've put %99 and then square bracket caret \n caret s. Now, this is getting into some of the more complicated parts of the format specification, but what this is saying is read in a string, it's still a %s, but we want it to be 99 characters long, and we want to allow it to include everything. The square bracket says is creating what's called a character class. We're saying allow it to include everything the caret is except for the new line. So in other words, the new line is what's going to end that string. Every other character we could type. And so this is actually safe, and it does not have the problem with not allowing the white space. So you might use something like this. Later on, we're going to use another function called fgetS, which allows us to do stuff in a little bit without using scanf like this. But right now, if you write a program and you want to get input, you can do it like that. And what this is going to do, it's going to fill in the string into that section there. All right, so let's quickly just go back to our program and try that. Oh, I forgot to turn on things so you can see what I'm doing. All right, so here's our program. So if you remember what we did, we said %99, and then open that, and then do caret \n s. Let's run it. Oh, I didn't change this back to 100. Let me change that back to 100. And so now I can type in, this is a test of this program. And now you entered, this is a test of this program. So it worked that time. Notice it did not abort it because it didn't detect the stack getting destroyed by us running off the end of this variable. And it would never get that even if I typed in 100 characters. So let's kind of continue on from there. Let me go back to okay. So now it won't overrun, and it will allow everything to be typed except the new line. And I see there's a typo there. I'm going to fix that one here. New line. Okay. Okay, so one thing that I need to tell you, and maybe you've already gathered this, never use an unguarded scanf call with a string specifier. So never do that thing where you say, hey, read in a thing, use a %s. Because that, if you don't have that guarded to have the size match up with what makes sense for the amount of space you have allocated, then you've left yourself a security hole in your program, and some hacker could overrun and walk off the end of that stack into other parts of memory and inject things in there, including code, or overwrite other parts of data in a running program. It just depends on what system that's on and what order the stuff is in memory. But you're giving somebody access to run off the end of an array into other things, which could either break the program or introduce some sort of security hole in that. So always have the size guarded on %s when you're using scanf, or fgetS too. Okay, the string length. As you might remember, we said that strings were represented by where they live in memory, or what address they're at in memory. And they're terminated by that 0 character, the null character at the end of that string. That's the only way that the string knows how long it is. So let's say we wanted to make a function that counted up how long the string was. Well, here's version 1 of that function. So we're making this string length function. We're going to pass a pointer to the string, a character pointer, the address of where that string is. and then it's going to return to us how many bytes long it was. So down here, we start basically a counter at 0. We say, well, the thing pointed to by that string is not a null. So in other words, if it's something that is not the end of the string, then go to the next character and add 1 to our count. So in other words, if I start and say, hey, that's not a null, add 1, go to the next space. Add another one, go to the next space. We're going to continue doing that until we get to the null character at the end. And then when we do get to the null character at the end, we immediately return the what was in I, what was in our counter. So in other words, that's not null, tick, add 1 to the counter. That's not null, add 1 to the counter. That's not null, add 1 to the counter. That's a null, my counter was 3, return that back to the person that requested. Now, I'm going to present a couple other versions of an implementation for this. But before I do that, take a look at this, make sure this makes sense. Remember, plus plus is increment, and if we use it on a pointer, it goes to the next item in that list. Since it's a character pointer, it goes from this first byte to the second byte, and the next time through the loop to the third one, the next time through the loop to the next one. So we're moving a pointer through memory. And that's a very C language-like way of dealing with things. Now, moving on, let's look at version 2. Now, version 2 is a little shorter. We still have our integer I, but I used a for loop here, and I say for I equals 0, and then I say st sub I. Now notice I don't have something that says while that's not equal to 0. I basically just have st subscript I. And if you remember, comparisons in C, all that matters is 0 is false, anything else is true. So in other words, what we're doing is we're saying if I look in this string at index position I, which starts at 0, so we start at position 0, and if I say, if I see something that's not 0 there, then that's true, so I continue through the loop one more time. And then at the bottom of the loop, I increment I, which is the same as kind of what we were doing over here. So when this empty loop gets done, st will have gone through every one of the positions in that string up to the null, and the count will be how many there were going up to that null, and we just return I. All right, so that's version 2. Now, let's improve it a little bit further. And I don't even know if these are really improving it. They might be making it less understandable, but here's version 3. Version 3 is doing the same thing, but now notice I'm not ever indexing that array. So when I do this indexing into this array, it has to do a pointer arithmetic and a thing pointed to by. Well, we don't even need to do that because we already have a pointer. So we could just say, hey, while the thing pointed to by st++, that's going to increment it. So that's a post increment. It's getting the thing pointed to by st, but also incrementing st at the same time. So in other words, this is going to look at it before, since that's a post increment, it's going to look at it before it was incremented. Give me what the thing pointed to by that is, which is going to be the first character in my string. But when I looked at it, if it wasn't 0, then the next time through, I'm going to be at the next one because I did a plus plus on that. And then my I is still counting up the count, and I'm going to return I at the end. All right, so final version of this, version 4. Notice what I'm doing here is I'm basically not even, I only have one plus plus, so this is actually a little bit simpler. So I made a character, I don't have a counter either. I don't have a counter for I. I'm just saying make another character pointer. And then what I do before the loop starts is I said copy off that other character pointer, or the st into this other character pointer. So think about we're making a copy of the address of where this thing started in memory. And then the next thing we're going to do is now we're going to say, look at the thing pointed to by st2. So we're taking the copy and looking at what it's pointing to, which will be the first character of the string. And if that is not 0, we continue on into the loop, which at the bottom of the loop, we're going to increment st2. So we're going to move it up. So in other words, if it was not null, go to the next position. If it's not null, go to the next position. If it's not null, go to the next position. And we will ripple through all of the positions until we see the null. And at that point, we've saved off where it started in memory. So we just say, okay, well, how many bytes were there from the start to where we are now? And we compute that using this pointer arithmetic with where we are now minus where we started. And that'll give us how many spaces we've moved from where we started. So this is a very C-like implementation for this. Notice it might be less understandable than version 1 way back over here, but it's also probably going to be more efficient because remember way back over here, Notice what we're doing. We're doing this not equal null every time. That takes an effort to load the null into memory, load the value that's in ST, that address, then get what's at that address and load it into memory, and then compare those two things. And then we have two increments inside the loop. Notice what we have over here in version 4. The only thing inside the loop, well, this loop is empty. The only thing that's happening every time is we're incrementing ST2 and then looking at what it points to. That's it. And we only do one subtraction at the end to compute that. All right. But the fun thing is that we don't really have to write string length at all ourselves, that it's already written for us. And I believe the standard implementation looks something like my version 4 here. If you're curious, you could kind of do strlen source code Linux or something like that, and you'll find the standard library implementation of it. It's going to look something like this. But the reason it's included in the standard library is that it's something that's common that you need to do. And so all of those common tasks that you would want to do a lot, you could write it yourself, or you could use the one that's in the library. And I would recommend just using the one in the library. To use it, you just do #include string.h, and then you can use string length anywhere you want without having to write it yourself. But it's going to work something like what we have here. Okay, string copy. So back to the question of how do we assign a string to some array, because we couldn't say like we did earlier, like AR equal double quote hello. That doesn't work. So how do we assign it? Well, we need a string copy function. And to show why this is an error, here I have character, this string 1. It's 10 spaces. It's a character array 10 spaces big. I've got hello in there. And then I made a second one called string 2. And then so I want to make a copy of hello into that one. So st2 equal st1. That doesn't work because, again, the name of an array by itself is the address. And this left-hand side here, we cannot change that address of where that thing lives in memory. So we need to copy all the characters from one into the other one at a time. In other words, we need to say, take the H, move it into this array. Take the E, move it into this array. Take the L, move it. Another L, move it. O, move it. Null character, move it. Now I have a copy. So we need to have something that does that. All right, so let's look at first implementation of that. And this follows what the standard string copy function looks like. It returns a character pointer of the string that was copied. It also accepts as parameters the destination where you're copying to, and then the source where you're copying from. So inside of this function, I created a character pointer called destination original, and then I made a copy of the destination into that original thing. And the reason for that is because, remember, at the end, this is supposed to return the string, a pointer to the string that was copied. So I'm going to save that off because I'm going to move destination ahead in memory. Now, there's something I need to fix here. So let me do that real quick. This is a word processing problem that the reason this got messed up. This needs to be, oops. Yeah, the word processor, when you type in code like that, it'll sometimes lose parts of it because it thinks anything wrapped in a star pattern is to be bold-faced. And then since I have a style turned on, it won't allow it to be bold-faced, so it just gets rid of the asterisks that I typed in. So anyway, let's look at how this works. It says while the thing pointed to by source, in other words, that's the thing I'm copying from. Again, it's null terminated. So we want to continue until that source pointer gets to a null. And then what we're going to do down here is we're going to say set the thing pointed to by destination pointer, which is where it's going to, set that equal to the source pointer, the thing pointed to by that. So in other words, if we have these two strings in memory, where it's going to and where it's going from, it's going to copy the first character over. But then notice as part of that, it increments the pointer. So the source moves ahead one character, the destination moves ahead one character, copies that over. Moves the source ahead, moves the destination over, copies that over. Source, destination, copy. And it's going to do that until it gets to the null character at the end. And as soon as it gets to the null character at the end, it stops. But we need to put a null at the end of our destination. So at the end here, I go ahead and put the null on the end of the destination. So it is null terminated as well. and then I return the copy that I saved off so that this function could return the thing that was copied, this pointer to the string that was copied. All right, so make sure you look at that. This looks confusing when you first see it, but essentially what it's doing is got 2 pointers, a source, a destination, and it's just copying the characters and moving them over kind of together each time. Now, that's version 1. Let's look at version 2. Now, version 2 is a little bit more efficient, and I'm going to fix my indentation problem on this. Hold on one second. Oops, that's not what I wanted. There we go. Okay, this version 2, notice I'm doing the same thing, but I'm doing it in the while loop. And that's more efficient because here I had to move the source, move the destination, do the assignment, and then go to the top of the loop and then say, hey, load this thing up, load a null up, check it. But what we're doing here is remember that when we do an assignment, the assignment evaluates as the value that was assigned. And the value that was assigned in this case is going to be non-zero until we get to the null. And as soon as I get to the null character, I'm going to copy it over. And then that's also going to return that 0, the null, which is going to cause the while loop to end. And now notice I don't need that destination equal null at the end either, because I copied the null, and I say, now that I've copied a null, the while loop, or that will evaluate as 0, and when the while loop sees a 0, it terminates. So notice how concise that is. Might be a little confusing if you're not a C programmer and are not used to seeing things like this, but it makes total sense to a C programmer once you learn it, and it's super efficient. And one of the things there that is important to note is that, let me fix this because it was on both pages. Oh, that's why it moved that over. I just got to move this back. All right, so that's a very C-like way of solving that problem where we're evaluating the increment on each of these, but since it's a post increment, we get the value of what it was before it was incremented. We do the thing pointed to by each of those addresses and copy the thing pointed to by this one to that one. So we're kind of moving the pointers and we're copying the data, moving the pointers all in one step. And notice that's going to be super efficient. So you might have a little hint there as to why C is so fast. Again, the other thing is that the increment operators, part of the instruction set of the computer, the dereferencing an address, part of the instruction set of the CPU as well. And so this is all using very low-level CPU instructions that you could not go really any lower than that. I suppose we can unroll that loop to some extent and get it to be a little faster. But this is going to be super efficient. It might be a little confusing until you learn C a little better, but this actually works really well. Okay, final topic of today is this whole idea of passing pointers. And the idea of passing a pointer is we're passing an address to some function. And we saw that previously with arrays. And we also might think of that for string. How do I pass a string to a function? Well, printf is one way to do that. Or back here, these character pointers. That's passing 2 strings in and having a copy from this one into that one. But the idea is that there's another advantage to passing a pointer to some data as well. And it can be useful for passing variables whose data we want the function to change. So since C passes everything by value, if we pass the value of an address, that gives the function access to the actual data itself. So the example there is, if I were to just show you a picture of my building, so I basically print out a picture of my building and I show it to you and say, here's what my building looks like. Then you could look at that, you could use it for something. But if I actually give you the address of my building and said, here's where my building is, you could go there and do stuff to it. And so the idea there is that's passing by address or passing by reference. And that allows us to change what is stored in that variable as we pass that to a function. So let's look at an example. All right, so here's an example where I'm passing in 2 integer pointers, and I want this function to switch the value. So if I were to pass in, for example, the address of a variable I and the address of a variable j, that when this function is done, they will have exchanged value. So if I was 10 and j was 20, after this, the 20 would be in I and the 10 would be in j. All right, so notice I pass in the addresses, or I would pass in the pointers to those things. When I would call this function, I would have to put ampersand in front of the two variables to get the address of them. But when I pass it in, notice I make a temporary integer. I say, give me the thing pointed to by that, which would give me the value of the first one. I save it off. I then say thing pointed to by that, the one I saved off, I now overwrite with whatever is in the second one. And then I take the temporary one and put it in the first one. And after this call completes, those will have swapped values. If I just passed in the values, I couldn't have done that. I have to pass in those addresses in order to do that. Okay, so passing by reference can also be more efficient, especially if we have a larger aggregate type like a structure that has a whole lot of data elements in it. And why is that more efficient? The answer is because we're passing just a single address. So for example, if I were to take a Post-it note and just write a single my address on there, and give that to you, you could go to my house and do things there and look at it and estimate carpet or whatever you wanted to do. But if that's a whole lot easier than me picking up the whole building and taking it to you and saying, here's this giant structure, I want you to give me an estimate on it. Or it's a lot easier than copying the entire thing and making a whole duplicate version of it and taking it to you. And the difference could be tremendous here, that rather than moving thousands of bytes or tens of thousands of bytes around in memory, to give to a function, we just give a single little piece of address data to it, and then it can access that directly. And we'll learn more about that later on when we talk more about structures. But what I want you to do today is go back and look at those examples of those string copy functions and the string length functions. Make sure you understand how those work. We'll probably have a quiz on something similar to that coming up, but I want you to look at that. But other than that, that's all I want to do today. So work on your labs. Everybody wash your hands and stay safe. And I'll see you next time, and we'll probably have another quiz, and we'll have another lab coming up as well. We've got a little more to cover before we get to the next lab, so it might not be next class, but the one after, but we will have a quiz coming up soon. All right, that's it for today. Thanks. See you guys soon. And if you have questions, email me, text me, give me a phone call, and if you need me to, I can come down and meet with you anytime.